Good afternoon, everybody. I'm Bill Tonti, and I manage the Future Directions group. Kathy and I work together, so I'm an IEEE employee, so you can throw darts at me, and hopefully I don't die, but we'll see. I'm going to talk about my past, though. So in my past, I'm a semiconductor physicist, because Kathy said talk about the past, the present, a little bit about the future. So I'm going to start with the past and kind of hopefully get you a little excited. So this slide I pulled off the internet. If you Google IBM eFuse, you'll find this slide out there, and I thought it was appropriate. eFuse was an element that I invented, I developed, I deployed, so I can take credit for it. I have no holes barred there, so that's the way it is. And what you're seeing is using the property of a reliability failure mechanism, which is called electromigration. We're taking an element on the left where it says anode and cathode. It says unprogrammed, which basically is a short circuit. Kathy's changing the slides a little bit. No, I'm on this slide. It's okay. Okay, so I'm looking at this element, which is unprogrammed, basically a short. I actually take it to the point of electromigration, and on the right-hand side, I don't really have a laser pointer here. Maybe this, does this show up? Yeah. I basically take this element in between the anode and the cathode, and I change its property. I turn it from a short circuit over here to an open circuit over here, and I can do all kinds of crazy things with that. So you can imagine, you know, as an engineer working in a semiconductor environment, taking something that is not supposed to happen and integrating it in a process flow. So that's what we ended up doing. And this actually enabled many technology nodes that started in this particular case in the quarter micron node to the current node of being able to produce imperfect chips and make them perfect by having this on-board capability, because you can do it at any point in the assembly once the design is complete. That wasn't the case in the past. In the past, fusing technology in semiconductors was called laser fuses, and you were essentially ablating metal, typically the last level of metal in the process. So you had one chance to do any kind of a repair or a change in the actual technology deployment. In this case, you could do it when it's in the product. You can do it in the field. As soon as the element is there, you have the ability to change it. So this allowed all kinds of paradigms. I'm going to read you something that I pulled off of this with the idea of what this was supposed to do. So this is coming from something that I downloaded by looking at the IBM eFuse. It says, originally conceived by IBM in the early 2000s, eFuses were intended as a simple way to alter the function and performance of a chip in real time, which is what they do. In other words, the company had designed a chip that could reroute chip logic much the way highway traffic patterns can be altered by opening and closing new lanes, according to Bernie Meyerson, who is now the CTO at IBM. The idea that a chip could regulate speed or power consumption issues by simply tripping a fuse, or more impressively, repair unexpectedly, potentially costly flaws. So that's what this did. It's still in use today. Every company that's on the market, you know, whether it's a foundry or a brick and mortar or a company producing, you know, specific products, they all use eFuse. So this became a very important technology element, and it actually made it into the consumer space. So I don't know how to change the slides here. I probably need Kathy to go to the next one. I'm not sure what she did, so maybe you can flip. I give you another slide to show. I want to bring this sort of to the, it's still the past, but it gives you an idea how this affected consumer electronics. So I also pulled this off of the internet. This is the Microsoft Xbox 360. So it's an older gen. It's the one that my group designed at IBM. So I know intimately what's going on with this particular CPU. And in this CPU, eFuse was enabled. This is a 90 nanometer. This was a 90 nanometer design. So we went a few nodes in the future at this point in time. And this was the first Xbox that IBM had designed for Microsoft. And if I read this, this is the interesting thing. Well, how did it really get used? You know, what's going on here? Now, I'm not claiming that this is true or false. You can figure it out yourselves. I'm just going to tell you what was going on in the discussion beds when this chip was released. It says, clearly Microsoft was employing eFuses in a very different and inventive manner than IBM had originally intended. But it raised a number of important questions with regards to how eFuses worked. Because these fuses were a hardware component of the CPU, many wondered just how many Microsoft had to play with. Would they eventually run out? allowing hackers to modify the system, but perhaps more alarmingly, a reverse engineer by the name of blah, 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 theorized that Microsoft could actually blow the CPU E-fuses in such a way that it may be possible to shut power off to the CPU permanently or increase the core supply to the point of self-destruction. So you can kind of take that to what you're thinking about in consumer electronics in terms of the capabilities that were introduced in this particular case. Now, whether I'm saying that's true or false, that's for you to figure out. I'm not going to say either way. But these things, which were high-tech implementations that were going into the kinds of things that we heard from our keynote earlier, whether it's in a GPU or an FPGA or an ASIC, they now made their way into consumer electronics, and they can do marvelous things. So that's kind of just giving you an idea of how technology migrates into the consumer space in the real world. I'm just wanted to point that out. I did say I manage the IEEE Future Directions Committee, and I will just name, so in the future, what are we doing? I'm going to name the initiatives that we're currently working on. I don't have a slide for that, but I can name them because I know them pretty much off the top of my head. So we have an initiative on blockchain technology, which is quite interesting. We're not approaching that from the perspective of looking at cryptocurrency, for example, which is primarily how blockchain became in there. We're also not looking at any of the devilish ways that people are extracting funds from you. So we're not looking at that, but we're looking at how to use blockchain in a computing paradigm. And it has a lot of barriers that need to be solved, that the technologists that are working on that in the initiative are actually investigating. I'll mention two of them because they came up also in the keynote a little bit today. So one of them is latency of the chain. In order to have blockchain work in a computing environment, you really have to solve the latency issue and have the chain be able to operate at the speeds that you're expecting your system to work at. So having a chain that works in seconds is not acceptable for a computing environment, for example. The other big issue of blockchain is the power requirements to run the chain. So to implement blockchain across an entire computing paradigm would probably take down the power grid of every country you put it in. So that's another area that they're looking at. How do you improve upon this? There are others, but I won't go into it. The next initiative that we're working on is an initiative called Rebooting Computing, and this plays into the semiconductor space. It's what happens at the end of Moore's Law scaling, which is, for the most part, here right now. The nodes that are being deployed, which are now down to about 5 nanometers, are at the point of which no one can shrink any further because the variability that results in producing traditional semiconductor products is much too high to actually deploy them in the field. It doesn't allow those products to function reliably or even at T0, if you will. So if I think of reliability as a function of time, or just in the deploying of those at T0, there are immense failures associated with scaling any further. So as the keynote mentioned this morning, there was all kinds of things going on with different kinds of integrating schemes of taking the best ASIC or the best GPU or the best CPU or the best photonics device and putting them in some kind of a heterogeneous stack. That's one of the solutions that this initiative has been working on. They've also issued a roadmap called the International Roadmap for Devices and Systems, which you can Google and find. It's a continuation of the semiconductor roadmap that existed in the past, which was called the International Technology Roadmap for Semiconductors, the ITRS. Maybe some of you recognize that acronym. It's now IRDS. But that roadmap issued last year, the first one, and it talks about quite a few inventive things that are going on in the semiconductor space to enhance, for the most part, the nodes that are there now. The next initiative that I'll briefly mention is an initiative which is looking at future networks that was also discussed quite a bit this morning. Primarily right now their focus is on 5G, and they're also developing a roadmap that takes you beyond 5G and is looking at what happens next, whether we call it 6G or 7G or 8G, but they're looking at what are the requirements as 5G becomes deployed, what are the next couple of things that need to be worked on. So that's a technical roadmap similar to the IRDS roadmap. Let's see. The next initiative that we have that I'll just briefly mention is one that's called the Brain Machine Initiative. It's actually called IEEE Brain, but it's the Brain Machine Initiative. And that one is actually bringing technologists, such as folks in the room, technologists across very many disciplines, and integrating those folks with neuroscience individuals and talking about what needs to be done on the EE and CS side that can enable the technologies of those capabilities. And since I only have 1 minute, I'll leave it at that. And thank you for giving me a chance to talk about the past, a little bit the present, and the future. Thank you. Bye.